All right, so now we're going to start reviewing the E&M portion, and we're going to start with electrostatics. And so at its core, remember, the whole point of electrostatics is we have positive and negative charges, and that introduces a new force, right, compared to mechanics. Mechanics, we haven't had any new forces. This is our first new force. This force can act at a distance, like gravity. It's a fundamental force, and it's given by this equation here. We have a new thing we call unit of charge. It's called coulombs. A proton or electron has this charge. Protons are positively charged. Electrons are negatively charged. They're the smallest unit of charge that there can be. You cannot have a fraction of this charge. This is the smallest amount of charge that exists in the universe. Okay, so like charges repel, opposites attract. So this force here, this equation here in force looks very similar to the force of gravity, but there's a couple of things we want to keep in mind here. One is gravity was always attractive forces. That means you were always pulled towards planets. Force always pointed directed towards the center of the planet or center of the object. Now, when we talk about electrostatic force or Coulomb's law, it could be towards each other or they could repel each other, right? The constant here is different, right? So it's based on the amount of charge, and it's also 1 over r squared relationship, just like the force of gravity. But K is our Coulomb's law constant as opposed to the universal law constant. Sometimes people write K as equal to 1 over 4 pi epsilon naught. I stick with K for almost all the times except for a few cases. It's just easier to write, and it's easier to remember this than this form. But just remember that this value here is K. Okay, now in terms of this is the only equation we've introduced at this point. We still do the exact same thing we did in mechanics, which is to do our draw our free body diagrams, apply F net equals ma. The only difference is we've introduced a new force. And the rules are two like charges will have forces pointing, this should be opposite, away from each other. And two opposite charges will have forces pointing towards each other. Okay? That's because opposite charges will attract, like charges will repel. Okay, then we talk about electric fields, and this is probably a lot stronger. In mechanics, we did talk about gravitational field being G, but now instead, like if we talk about force of gravity, you said it was like M times G, and this G was we called the gravitational field. And what was nice about the gravitational field is on Earth, for example, the force of gravity is equal, it varies based on the mass of the object, but the gravitational field was created by the Earth. So the force of gravity was based on the mass of the object and then something from the Earth we call the gravitational field. And so the G was universal for all objects on the Earth, right? It's the same values, 9.8 when you're near the surface of the Earth. It's the same for all objects. And similar thing for electric field is that there's a relationship between force and electric field. It's instead of mass, it's charge. But the force, the electric force, is equal to Q times something we call the electric field. And the electric field is created, just like gravity is created by the planet, by all the other objects, the electric field is created by all the other charges that are out there in the universe. Okay, so if I place a charge somewhere and I want to know the force that's acting on that charge, I take that charge times the electric field it's within. Now, the electric field for a point charge is kq over r squared. So it's just like this G was just G mass over r squared, if you remember this from mechanics. Very similar. You just drop one of the charges from Coulomb's law because you're dividing out that charge, and that gives you the electric field. Now, this is caused by other charges. So if a point charge creates an electric field kq over r squared. If you have multiple charges, a charge distribution, you may have to integrate it. You may have to chop it up into little pieces and add them up. Now, keep in mind, electric fields are vectors, so you need to add them as vectors, not add them as scalars. Adding them as scalars is you just add them up. Add them as vectors, you must decompose into the x and y components and only add things in the x or y components. Okay, you might see something called electric field lines. We draw these diagrams. We didn't draw them in mechanics because we didn't have multiple planets, planetary systems, and talk about multiple objects in the gravitational. We usually had one object, but we may have multiple charges, and we may want to see how the field lines are drawn. They are drawn from positive to negative charges because electric fields are vectors. The rule for an electric field, and this is the rule I help you. If you don't remember the direction, if you're just like, oh yeah, it's a vector, but how do I remember? Electric fields point. They are a direction that a positive charge would experience a force. That is, if for any spot that I care about the electric field, and I don't know the direction of it, right? If I were to place a positive charge there and think about the net force that acts on there from the electric force, from the electric field, then the direction that that force points is the same as the direction of the electric field. Okay? And remember, you got to sum them up like any other vectors. Okay, Gauss's law, arguably the most important part of electrostatics, the most thing that you'd be tested on, probably the hardest thing for most people to understand, is to make sure that you understand Gauss's law. So the left part of this integral here is we call the flux integral. It is a dot product between the electric field and the area vector. So that means if I have a surface and electric flux is like, I'm trying to think about how many of these imaginary electric field lines are piercing the surface here. What I want to do is, this is maybe the electric field, and then the dotting it with the area, if you think about a little chunk here, the area vector is perpendicular to the surface here. Okay, and so you're just going to multiply. But if you think about here, and this is our dA vector, it points perpendicular to that surface, and we want the component parallel to that. Okay, so that's why, and the way you want to interpret that is it's the amount of electric field that pierces through the surface, and you want to pierce it ideally at a right angle, or you need to find the component that's going to pierce the surface. So that is, if the electric field kind of runs parallel to the surface, then it doesn't contribute any flux because it's not going through that surface, right? And this integral is tricky, right? Like, you don't know a lot of vector calculus. You can't compute this integral, so this needs to be done very simply. But it's related to the enclosed charge. So when we do, this is why you put a circle here on this integral, because it's a closed surface. So you think about, you've surrounded a charge or a group of charges, and all you have to do is count up how much charge is within that surface, and that's going to give you a relationship with the total flux. Okay? Now, there are tips for choosing a Gaussian surface. This is a super important part. In order to make this left side of the integral computable, without actually knowing vector calculus, you need to choose you need to first know the direction and the symmetry of an electric field. So for example, if we take a point charge, for example, and its electric field is going to point away from the positive charge, and it's going to do it in radial directions. In 3 dimensions, it's going to be a ball, and it has radial field lines pointing perpendicular and away at all points. Okay? So what the symmetry is, first off, is 1, you need to know that it radially points outwards. And then 2, you need to know that as you rotate it, it's got to look the same, because it's a spherical charge. If I rotate it, it shouldn't, like everything, it should be the exact same configuration as was before. Right? So that's the symmetry of it. So when I'm choosing a surface, I want to make sure that the electric field either passes through the surface parallel, in which case the flux is 0, or perpendicular, in which case the dot product is very clear. So in this case, that's why I pick a spherical object as the symmetry for my Gaussian surface. The reason is because then it's perpendicular, because I know the electric field is radially outward. If I instead had pointed like a cube, for example, like let's say I pick like a cube as my Gaussian surface here, like the problem is the electric field is going to pierce it at different angles as it kind of passes through the surface, right? It's not going to always be perpendicular. So that's going to be very, very difficult to compute this integral. But the sphere is nice because the electric field is 1, perpendicular to the surface, okay? And then 2, it has the same amount. If I centered it around that charge, then the electric field should be the same magnitude everywhere on the surface. So that integral becomes a lot simpler. Okay, so let's go through a few practice problems here. So we have a sphere of uniform charge density, has a positive net charge plus q in radius rs. So we have a sphere, has a plus q charge and a radius rs. Small particle of charge positive q can be moved through space both inside the sphere uniform charge and outside the sphere. When the particle held in place at the center of the charged spherical region, so we have a positive charge here, what is the magnitude of the net electric field due to the particle and the sphere at a distance rs over 2 from the center of the sphere? Okay, so you have 2 charged particles, and let's make this a little bit bigger here. So we have a sphere here, right? It has a distance rs. It has a plus q charge. And then we're thinking about, we have a positive charge here that is positive q. And I want to know the electric field at this point. Okay, at rs over 2, right? We'll put it right here, the electric field at that point. Okay, so what are we going to do to try to compute this is we're going to think about, because this is a charge density, you could try to set up an integral, but we'll just use Gauss's law because of the symmetry. Because it has spherical symmetry, we expect the electric field to emanate outwards, if I draw a sphere here, at the same amount everywhere. Right? So this is the Gauss's law and why we're going to use it, because we expect the electric field to point radially outward, right? Due to spherical symmetry, right? Like, why would it point, if it's not radially outward, then if I rotate it, it will look kind of weird. So it needs to point away from the center just due to that symmetry here. Okay, so now we're going to compute E dot dA equals the charge enclosed over epsilon naught. So let's take it one step at a time. First, compute the electric flux. Well, because the E field is already perpendicular, you can just multiply the E times the area. And because it's constant over the surface, this just becomes E times the area. And that's because of our chosen surface. It's not always just equal to this. That would make this integral very trivial if this were always true. It's because we picked the surface for that reason. So it's the electric field there times the surface area. Surface area of a sphere is 4 pi r squared. Well, yeah, we'll use r, where r is going to be rs over 2. Okay, so we'll do that for now. Now, the enclosed charge we have to think about. All right, the enclosed charge is you've enclosed this positive q, but you've enclosed a portion of the positive q as well. It is a uniform charge density, so all that matters to get the amount of q is to know how much volume we've enclosed. So the charge enclosed is going to be q, right? This is a positive q charge, plus some fraction of big Q, which is the fraction of the volume because it's a uniform charge density. So we're going to think about how much volume did it take up? Well, it took up 4/3 pi r cubed divided by, that's the volume of what I've enclosed, divided by the entire volume of the sphere, which is rs cubed, like that. Okay, divided by epsilon naught. Okay, and so now we can now plug in r is equal to rs over 2. So we're going to electric field times 4 pi rs over 2 squared is going to equal q plus this 4/3 pi cancel. This is going to be q times, if I cube rs over 2, it's going to be rs cubed over 8 over rs cubed over epsilon naught. The rs cubes cancel, and this becomes 1/8. This, if I square, becomes 1/4, so this would be electric field times pi rs squared is going to be q plus 1/8 big Q over epsilon naught, and then you divide that over, and you end up getting electric field is q plus 1/8 big Q over pi rs squared epsilon naught. So it just becomes a math problem at that point. They didn't simplify it quite that, but the plus 1/8 Q is over here, and all they did over here was just handle the rs over 2. They didn't actually square that part out, but A is going to be our correct answer because that has the correct enclosed charge. Okay. All right, let's take a look at Gaussian surface in the shape of a side cube of length A is oriented 1/4 of the origin. The cubical surface is a region with charges. The electric field is described by Bx times I hat. I hat being the x direction, so we're going to have it in this way. It's going to be Bx based on the coordinate going through here. What is the total electric flux through the surface of the cube? Now, the electric field is only pointing in the x direction, right? So what's happening here is there's no electric flux on this side because it's related to the x coordinate. So you got to think about, here is x equals 0, and there's no electric field during to there because if I plug in 0, it's just going to be 0. So it's 0 on this surface. On the top, there's electric field, but it doesn't pierce through the surface, right? So on the bottom and the sides, it's only going to pierce through the surface right here. That's the only area where the flux is actually going to go through, right? If I look at, sorry, let me color it with a different color. This is the only side that the electric field is going to pierce through, because it's either going to be this side, or I mean both technically, but this side doesn't have any electric field because the x is 0, so only the flux here, right? So this, what is the electric field here? It's going to be B times the x coordinate. Well, the length is A, so it's B times A. And then you just do that times the area, because it's the same electric field everywhere along that surface because the x coordinate is the same everywhere along here. All of this is x equals A, right? So it's just BA times the area, which is A squared. So it's going to be BA cubed. So it's going to be B. All right. Two small charges are arranged along the line have charges -3Q and +4Q. tick marks on the equally spaced, which labeled tick marks as the electric field, have the greatest magnitude. So electric field, we want to think about the electric field. Now, electric field from a point charge, because these are point charges, is kq over r squared. Now, we've got to add them up like vectors. Okay, it's an important part. So we need to think about any point, we need to draw the direction of the electric field. Now, it is the direction that a positive charge would experience a force. So at point A, it would experience a force to the right from this charge. Okay, and then from this charge, it would experience a force to the left. Why? Because if I put a positive charge here, it's drawn to this charge and it's going to be pushed away from this one. Okay, so these are moving opposite directions, so it's probably not going to have the greatest magnitude necessarily. Let's put a positive charge here and think about it. Well, again, you're going to be drawn towards this charge and away from this charge. So there, the electric fields are going to add to the left, because if I put a positive charge here, it would experience a force to the left from this guy, because it's opposite charges, and they would be attractive. And this is a positive charge. It would be repelled by this charge, so also to the left. So it's not going to be A. Could be B, because they're adding together. That would be good. How about C? C is going to be drawn towards this one, and it's going to be pushed away from this one. So C and B are both options. And then D is also going to have it to the left and to the left here. Now, in order to add them up correctly, we need to now think about what is the contribution of the electric field, and then numerically kind of figure it out. And notice that these marks are like, this is like, each one of these marks is like 1, right? So this total electric field, because they're both, for B, C, and D are pointing in the same direction, we can just add them up, right? It's going to be K times 3Q. And don't put the negative charges. When we do the electric field, ignore the sign of the charge. We handled the sign by drawing the correct direction of the arrows. So my recommendation is not to plug in the sign into here, but to just point it the correct direction based on your free body diagram. Okay, and then just assign the sign based on which way you define as positive. So we'll just make left positive because all the arrows are pointing to the left. So we'll just make everything positive there. Now the distance from there to there is 1, so we'll just make it 1 squared. Now it's not exactly 1 meter, but it's proxy for whatever the unit of 1 is. So we might as well just say 1. Plus K times this charge, 4Q, also pointing to the left. And how far is that away? 1, 2, 3, 4, 5. 5 squared. So this is going to be 3KQ. Plus 4/25 kq, and you can see how this is. So this is the electric field at B. How about at C? It's going to be K3Q, and what is that distance? Going to be 1, 2, 3, 3 squared, and then K times 4Q over, what is that? 1, 2, 3, also 3 squared. So this is going to be 1/3 kq plus 4/9 kq. Okay, and then at D, it's going to be K3Q. What's the distance between D and this charge here? 1, 2, 3, 4. 4 squared. Plus K times 4Q over 1, 2. 2 squared. Right? So this is going to be 3/16 KQ plus 4 over 4. That's just 1 KQ. Now, this one has a 3 KQ, which is already bigger. This is like 1 and something. This is like less than 1. Yeah, this is like 7/9. This is definitely going to be the biggest, right, from there. And that's because you can intuitively get it because you're just like, well, it's 1 over r squared, so it's closer. But might as well just numerically compute it based off of what we know there. Okay. All right, let's go through some FRQs here now. So students perform an experiment to determine the vacuum permittivity. Sphere 1 is a non-conducting sphere with charge positive Q attached to an insulating rod. All right. Sphere 2 is a non-conducting sphere with positive big Q and has a mass m. Sphere 2 is hung from a string of negligible mass of length L. Sphere 1 is brought near without touching. Sphere 2 is shown. Equilibrium established when the centers of the two spheres are the same vertical position and horizontal distance d apart. String at an angle theta from the vertical. Derive the relationship between the distance d and the angle theta to show that this is true. So whenever they give you the derivation result, kind of a sign that it's a little bit tricky, so they want to make sure that you know how to do it. So what we're going to do is we're going to start with a free body diagram. Let's think about the forces on this thing, right? So this guy, he's going to have gravity, mg, and then the rope's going to touch him, so then he's going to exert a tension force in this direction, which is at an angle theta. And then there's an electrostatic force. They're both positive charges, so they're repelling. So from this guy's perspective, he's going to be pointing to the right. Right, which is the electrostatic force, so we'll get to in a second. All right, cool. So we've drawn our free body diagram, so we're done. We're done with that. Next step is identify the acceleration. Well, they're just hanging here, so the acceleration is 0. So we know that the net force is going to have to be 0 ultimately. We do need to decompose the forces though, right? This is t cosine theta. This is t sine theta. And now we need to look at the x and the y directions and talk about the forces. Because the net force is 0 because the acceleration is 0, that means the right forces have to equal the left forces. And the vertical forces have to equal each other. So the upward component has to equal the downward component. All right, now the electric force, this is where we're going to now use what we've learned. So everything we've done so far, for the most part, is stuff we've done in mechanics. But now we're going to use the Coulomb's law, which is K, and then we talk about the two charges, Q, big Q. What's the distance between them? D squared. That is the electric force. That's going to be T sine theta. Oh, sorry. Oops, one of these should be cosine theta. The vertical one is cosine theta. My bad there. Okay, and now we want to get rid of T. Right? Because we need to, so let's solve for T, because T is not something in our answer. It's mg over cosine theta, which we can plug into here. So that's going to be mg over cosine theta times sine theta. And remember, sine theta over cosine theta is tan theta. Now we want to solve for D, so we can move the D squared up. Let me just kind of KQ over D squared. I can move the D squared up and move that to the other side. So D squared is going to be K little q big Q over mg tan theta. And therefore D has to be the square root of that. K little q big Q over mg tan theta. And that completes our, okay, they use epsilon naught for, the K. You can do that as a last step if you want. Replace the K with 4 pi epsilon, 1 over 4 pi epsilon naught. Because remember, this guy here is K, right? Okay, let's take a look at another problem. So non-conducting sphere, uniform volume, charge density surrounded by thin concentric conducting spherical shell shown in the cutout view. So this thing, the sphere has a charge of minus Q. So this is a non-conducting sphere, so this is minus Q. It's uniform volume charge density. And this thing has the shell itself has a positive Q, and then this thing has a negative Q throughout the sphere. The radiuses are R and 4R. Using Gauss's law, derive an expression for the electric field at distance R from the center of the sphere for R less than R. That means we want to talk about in here. So we're going to talk about a Gaussian surface that's spherical in there. Why spherical? These are all spherical charges, so we expect by symmetry the electric field to be radially outward or inward. It could be outward or inward. It just depends on here, because you're closer to negative charges, actually probably going to point inward, because electric fields, so technically it's probably pointing this way, inward at this point, because you're being drawn towards a negative charge. If I put a positive charge here, it's going to be drawn towards a negative charge and away from this positive charge. So it's technically pointing inward. Doesn't matter for the magnitude, though. So we pick a spherical one because of that radial symmetry, right? So when we do Gauss's law here, is charge enclosed over epsilon naught. You want to think about, okay, so this is E, because it's just E times the area, and the surface area of the sphere is 4 pi R squared. And that is the charge enclosed, right? So how much charge do we enclose? Only a fraction of it, right? So if enclosed the negative Q. Now, should you put the negative charge? You can if you want. Technically, I already have the direction oriented based on the way I drew it, so I'm just going to say Q, even though it's technically negative Q. But again, direction's always handled just based on your free body diagram and your understanding of it. I don't use the charge values to determine direction of vectors, okay? That'll be different when we do potential, right? But for vectors, which is potential being a scalar, which we'll talk about in the next unit review. But for vectors, I always think about, I want to know the direction of the vector, and I will assign positive or negative based on what direction I want to say is the positive or negative direction. So it's not we're not enclosed the entire charge. How much charge is enclosed here is the fraction of the volume, right? So it's 4/3 pi R cubed divided by the entire charge of the sphere, or the entire volume. So that ratio is the fraction of Q that's within that surface over epsilon naught. Okay, so this 4/3 pi canceled. This ends up being Q R cubed. You can bring the big R down onto the denominator. And then we're just going to divide by 4 pi R squared. So again, the electric field is going to be Q R cubed over 4 pi epsilon naught R squared times big R cubed. So that will cancel with that. And so you get QR over 4 pi epsilon naught big R cubed. Okay, notice that that 4 pi epsilon shows up, so you could write it as K if you wanted to. But I already wrote it, so I'm not going to write it as K. Or you could write it as K big Q little r over big R cubed if you wanted to. Okay. All right, so that's how we use Gauss's law in that situation. Okay, let's take a look at this one. We have a very long, thin, non-conducting cylinder of length L is centered on the axis shown above. It's very long. The cylinder is a uniform charge density lambda. Point P is located on the y-axis for y equal to c. Derive an expression for the electric field at point P. Now, we want to know, so it's super long. So what we want to think about is the symmetry again. What is the direction of the electric field happening here? Well, this is a positive charge. It's going to point away and radially outward away from it because it's a long wire. And so if it had a component this way, it would be a little bit weird because I could flip it upside down and then now it's pointing down. But if I flipped it, it's the exact same wire. So is it up or is it down, right? So therefore, it has to be radially outward. It can't have a y and x component because if I flip it, it's got to look the exact same because it's symmetrical. Because if I flip the wire, it's the exact same thing. It's a really long charge, wire of same charge. So it can't have an upward or downward component. And it has to have a radial component. It has to point outward radially because as I spin the wire, it's got to have the same electric field everywhere as I spin it because it has that circular symmetry. So the way you want to think about it is the electric field has a symmetry and it's kind of going around the cylinder, or it has a circular symmetry. If I draw something like this, then it's going to be radially outward on that thing there. So what Gaussian surface do I want to use? Is I probably going to use a cylinder, all right? Cylinder of length L. And that way, the electric field is piercing that surface perpendicular at every location. Okay? So, now we're going to do our E dot dA. And you just want to break each part and think about how you're going to handle each part. First, think about this integral, and then think about how much charge we've enclosed. Okay, so I've made up a length. Actually, let's not call that L. We've called it L. Let's make it super thin, by the way, because this is really long. So let's think about a very, very small cylinder. Why do I want it very small? Because I don't really want to worry about what happens at the ends. At the ends, the symmetry begins to break. Okay, so we want to think about a very small. So we'll call this distance d, and it's very tiny. It's a very, very thin shell there. Now, because the electric field's about uniform over there, because it is a very long wire, we can say that the electric field here is going to be E times this lateral surface area. It's not going to pierce through the top ends here because the electric field is radially outward. So I don't need to worry about like the front side of those cylinders. I just need to think about the lateral surface area, and that is 2 pi r, okay, times the circumference of the circle times how wide that is. That's d. And that is going to be, the radius is going to be just c. So it's 2 pi c times d. Okay. Now that equals the charge enclosed over epsilon naught. Now, it's a linear charge density. So what a linear charge density means, it means the charge is equal to the density times the length. Now, the length of this thing is d. So this is going to be just simply lambda times d over epsilon naught. And what we see is that the d's cancel, which is really important because that d is something I made up. So then the electric field is going to be lambda over 2 pi c epsilon naught. So we can use the symmetry because it's very long here. Okay, it's a very, very long wire, and it's symmetrically around this point. Okay, now let's talk about what happens if we were to do like a case like this. Now we're off center and there's not any symmetry anymore. Now there's no reason to necessarily believe that the electric field is pointing up. It still has the circular symmetry because if I rotate it, it's still good. But there's no reason to think that it's necessarily more because I could flip it around. Like it's this way, I could flip it around and it's not symmetric. It doesn't look the same because of the fact that we're not centered here. So in this case, I can't use Gauss's law because I don't actually know what the direction is going to be, right? And if I don't know that direction, then I can't do that. I can't pick a Gaussian surface where it pierces it perpendicular. So can't use Gauss's law, or at least it'd be very difficult to use Gauss's law. It would require a lot more calculus than you're expected to know for this exam. So here we're going to do the more traditional part, is to say, oh, the electric field from a distribution is k dq over r squared. We could have done this for the previous one, but you're going to see that this is a lot more work. So there's a reason we don't always want to do this. This is always possible to do as long as you can chop it up and do the integral correctly. But Gauss's law saves you a lot of effort. This is a lot simpler. This is, you're going to see here, going to be a lot more work. Now, how does this operate? You want to chop it up into little pieces, right? So we're going to think of it as a whole bunch of tiny point charges put together. So we're going to chop this thing up into a bunch of little point charges. Each point charge has a length, we'll call it dx, because it's on the x-axis, right? And its location from here to here is the r. Okay, and remember, got to think about the electric field. The electric field is a vector, so I got to think about this component here. So this is the contribution of this electric field from this point charge right here. Now let's establish a coordinate system. This is going to be x equals 0. So over here is x equals negative b, and this is x equals a. And therefore, like if you look at dimensions, then this distance from here to here is going to be x. This distance from here to here is y. So you actually know what r is. So let's take a look at first. We want to think about the contribution electric field. Now we need to think about the x and the y component separately. So we need to add the x and the y separately. So this is going to be, let's make this theta. This will be dE sine theta, and this is dE cosine theta. Okay, so let's do the x components first. Okay, so we're going to find the electric field due to the x components here. So we're going to say like, okay, so that contribution, dE, let's see, sorry, I have it backwards, I think. This is sine theta, this is cosine theta, based on the way I set up the angles. This one here is cosine theta, and this one is sine theta. So the x component, we're going to do sine theta. dE sine theta, right, is going to be k dq. dq is going to be lambda. The charge here is lambda times its length, because it's a charge density. Lambda times its length, which is dx. And then the distance is r squared. Now, what is that r squared? In terms of these coordinates, it's going to be square root of x squared plus c squared. Right? Because this is actually a constant. Now, x varies, but the y value actually luckily is the same. So that's going to be c here. Okay? Now, times sine of theta. Now, this angle, if you look at this angle is theta also. So sine of theta from this right triangle is going to be opposite over hypotenuse. It's going to be x over r. Actually, this thing is squared. And then r, we said, was the square root of x squared plus c squared. So if you look at this, the dE and the x component, in terms of x, is going to be k lambda x dx over x squared plus c squared. So this is the first power, and this is to the 1/2. 1 plus 1/2 is 3/2. Okay, so that's the x component. So the electric field in the x component is going to be integral from negative b to a of k lambda x dx. I should have done an expression including integrals. I meant to say, like, you don't have to evaluate the integrals. This is supposed to set up the integral, but you can see how tricky this is going to be. X squared plus c squared to the 3/2. This integral is solvable, okay? But you know, like, that's beyond, that's like not necessarily the scope of this one. You can do a u substitution on this one to do this one if you really wanted to. Now let's look at the y component and set up the integral on the y component. So that's going to be dE cosine theta. So it's going to be, if we think about the dE in the y component, okay, that's going to be k lambda dx. It's going to be the same thing here, x squared plus c squared. So this part's the same. But now it's cosine of theta, and cosine of theta is c over r. It's going to be c over the square root of x squared plus c squared, right? Because cosine of this angle is going to be this over this. So then it's going to be k lambda dx times, or let's put the c in front, c dx over the square, or x squared plus c squared to the 3/2 power. Okay, and then we're going to integrate this from negative b to a. So that would be the components of the electric field. And if you want the magnitude of the electric field, it would be the square root of the x component squared plus the y component squared. Again, you don't have to worry about evaluating the integrals for this review. I'm just sort of saying This is how you set it up. And as you can see, how much more, we didn't even able to get to the solving, but how much more complicated it was compared to Gauss's law. But we couldn't use Gauss's law for this one. I'm not saying you can, I'm just saying we try to use Gauss's law when we can, because it can save you quite a bit setting this up. This is just a single length of point charge, uniform charge density, not even that complicated, but still the setup for the integrals are very tricky. Okay, this integral you can't solve without trig substitution, which is not a technique you learn in BC calculus, so you'd have to learn that independently if you wanted to evaluate this integral by hand. Okay, all right. And so that's just to illustrate kind of how you set those things up for electrostatics, okay?